In this video, we'll look at damped harmonic motion. So in the last video, we looked at simple harmonic motion. That is, we looked at any kind of behavior that can be modeled simply by using a sine or a cosine. However, the world does not really work that way, right? We know that if we pull a mass on a spring and let it go, it's eventually going to stop. It's going to come to rest. And that's true with many real-world scenarios. And so damped harmonic motion will be a way that we can model more real-world scenarios more realistically. So we'll talk through the intuition of damped harmonic motion, and then we'll go through a formal definition. So to begin, consider the equation for simple harmonic motion. Y equals A sine omega t. Now, suppose that I don't know what the omega is, but just suppose that it oscillates, completes one period between 0 and 2. So we would draw something like this, that. But like I said before, this kind of equation and graph doesn't really model real-world scenarios. So what we want to do is we want to modify this equation somehow. So what I propose is this. What happens if we change the amplitude here, this A? What if that were a variable? What if I plug in something like A minus t? So now our amplitude is determined not only by a constant, but a constant less some variable amount determined by our placement on the horizontal axis. And the intuition is this. So if we start at A, or if we start at t equals 0, this first part of our equation, which would be the amplitude, will be A minus t, which would be just A minus 0, which would be A. If we go over along some amount, I don't know what A is, but we're getting A minus t is just a line with a negative slope. So maybe we keep decreasing like that. And it's useful for us when we're trying to graph a sine curve or a cosine curve with a variable amplitude to look at this, which determines the amplitude, and graph this line in both its positive form and its negative form. So I might say y1 equals A minus t, and y2 equals negative A minus t. So we end up with a positive slope. And then these two lines might look something like this. So we start up here and end down here. And we start over here and end down there. And then if you're trusting your intuition, you might think that, okay, well then, if this is what determines the amplitude of our sine curve, then we can just kind of draw the sine curve into these two lines. And that would be correct. You could start here, and then like we said before, we've got a period maybe of 2, so it completes one oscillation in 2, so it goes up, and then back down, and into the 2, and then it goes on like that. And this is how we would draw something with a variable amplitude, a sine or a cosine with variable amplitude. So this is the intuition behind damped harmonic motion is instead of a constant amplitude for our sine or cosine, we're introducing a variable amplitude. And then we look at that variable amplitude, the equation for it, in this case, A minus t, and then we just draw that sine or cosine into those two lines. So with this in mind, let's take it a step further. So previously we considered a linear amplitude, a linearly decaying amplitude might be a better way to phrase that. So as we learned when we were exploring logarithms and natural logarithms, we learned that the world doesn't often behave linearly. So we happened upon the mathematical constant e, and we happened upon the natural log. And that constant will come back into play here. So now I have an equation, f of x equals ke to the negative ct. And kind of our simple harmonic motion equation, g of x equals sine omega t. let's say h of x equals f of x times g of x. So then if we were to draw this like we did before, let's first draw the f of x. So ke to the negative ct, these are general constants. Don't want to get too bogged down in it for now, so let's just consider if we have e to the negative t. So that might look something like this, right? We know that a base e with a negative exponent means that it's decaying. We have exponential decay instead of exponential growth. And then we'll draw our similar one like this. And now let's draw sine of omega t into this. We'll just say that we have a period of 2 like we did before. So that looks like this. Etc. and so forth. This happens to be a really good way to model real-world scenarios, like, for example, a vibrating guitar string or a vibrating violin string, where if you pluck it, it's not going to vibrate forever. Eventually, it'll decay. With that in mind, we can define a couple of equations for damped harmonic motion. For damped harmonic motion, if the equation describing the displacement y of an object in time t is y equals ke to the negative ct sine omega t, or y equals ke to the negative ct cosine omega t for c greater than 0. We need c greater than 0 just by definition so we can keep the negative in the exponent. Otherwise, if c was less than 0, we'd have exponential growth, which that doesn't go well with the definition of damped, like something slowing down. Then the object is in damped harmonic motion. And c is the damping constant. This is usually given to us. We could also find it depending on the context. K is the initial amplitude, and 2 pi over omega is the period.